Hello, my name is Nicholas Scaglione, and on behalf of all authors, I will be presenting EasySave, an evaluation of easy-to-deploy source address validation policies. IP spoofing is a technique exploited in many attacks, including distributed denial of service or DDoS attacks, DNS poisoning, TCP injections, and all other off-path attacks. IP spoofing is when an attacker sends data packets with a modified source IP address that it is not authorized to use. The defense against IP spoofing is source address validation, which validates the source IP address of incoming data packets based on some policy-specific criteria. On the internet, SAV policies are deployed at autonomous systems, or ASs, which are networks managed by a single administrative entity, such as your internet service provider. These ASs exchange reachability information via the Border Gateway Protocol. For the SAV policies we evaluate in this work, they use these BGP announcements to construct their filtering list for incoming data packets. We focus our evaluation on easy-to-deploy policies, meaning they don't require any additional communication between ASs or hardware changes. They just require changing the local filtering rules of the AS. This includes the unicast reverse path forwarding policies, or URPF policies, which are standardized by the IETF, as well as BAR-SAV, which is an internet draft in the SAV networking group. I will give a brief introduction to each of the SAV policies we evaluate in this work. Strict and feasible path URPF are two of the earliest SAV policies which were standardized. Strict URPF, shown in figure A here, will only accept packets if they arrive on the same interface that the router would use to reach the source IP address, meaning that strict URPF only works in symmetric routing conditions. It has no tolerance for asymmetric routing, which is very common on the internet. This leads to the main problem with SAV policies, which is false positives, or when it filters legitimate non-spoof traffic. Feasible path URPF, shown in figure B, attempts to minimize the false positives caused by strict by accepting packets if they have a possible path on that interface. So rather than the best path, it's just any path. The problem with feasible path is that it doesn't handle the situation in which an AS originates multiple prefixes to different providers. This motivates enhanced feasible path URPF, or EFP. The EFP RFC defines two algorithms, A and B, both of which address this limitation. The difference between the two policies is that EFP-B was designed to handle an additional situation in which the origin AS does not announce anything to some providers or uses a no export community for all announcements to some providers. BAR-SAV further improves upon enhanced feasible path URPF by incorporating BGP announcements, route origin authorizations, or ROAs, and autonomous system provider authorizations, or ASPA records, to help reduce false positives. BAR-SAV uses a modified version of EFPA, which, as we can see from figures A and B, handle the same situations as EFPA and EFPB. Additionally, as seen in figure C, BAR-SAV can use this additional ROA and ASPA information to handle the situation in which a provider uses a no export community or does not announce any announcements to all providers. Additionally, BAR-SAV handles direct server return, or DSR, which is a routing configuration in which the traffic originating AS does not announce a source IP address. This is seen in CDNs when a user's request is sent to a CDN server, but the CDN chooses to respond using a closer edge server to the user. BAR-SAV will allow these response packets, assuming that the edge server has a valid ROA for that source prefix. There are many more variants of these SAV policies that I will not discuss here. Some examples that you'll see later in the results is EFPA with bilateral peers. This is a simple extension to EFPA, which normally is only applied on customer interfaces to include both customer and bilateral peer interfaces. Additionally, BAR-SAV has an extra algorithm for provider interfaces called BAR-SAV PI. We evaluate both BAR-SAV with BAR-SAV PI and BAR-SAV without BAR-SAV PI. For this presentation, we will only show the results with BAR-SAV PI. Please see our full paper for our full findings. With that, the goal of this work was to evaluate these easy-to-deploy SAV policies on an internet scale topology and measure both the false positive rate and the detection or true positive rate. Additionally, as we saw in the examples before, the export behavior of the Origin AS has a major impact on policy performance. So in addition to simulations, we performed a measurement of traffic engineering methods performed by ASs on the internet. We used that data to then inform our simulations. The traffic engineering methods we measured are as follows. Export to all is very simple. You export all prefixes to all providers. Partial export to some is you selectively export a subset of your prefixes to some of your providers. This can include announcing a super prefix or a separate prefix to the remaining. No export to some is when an AS does not export anything to one provider or uses a no export community. Finally, there's AS path prepending, which is shown in figure A with export to all. This is when an AS prepends their ASN to the AS path multiple times to deprefer the route. And while it is shown with export to all, it is independent of the prefix and therefore can be applied with any of these prefix traffic engineering methods. For this measurement, we use CADA's AS topology together with routing data from RIPE and route views BGP collectors to measure the behavior of multi-homed edge ASs. One limitation of this measurement is that for no export to some, if either it's a lack of announcements or a no export community, these announcements are not propagated to these collectors, leading to an underrepresentation of these. In order to address this, we also conducted a network operator survey. We surveyed RIPE, NANOG, and other network operating groups and only received around 31 responses. But with that, we still received some validation that traffic engineering is widely deployed in practice, with 83% of operators reporting using some form of traffic engineering. Additionally, 40% reported using no export to some, which is significantly higher than the 2.3% seen in our measurement. Additionally, 30% reported using partial export to some, and 70% reported using AS path prepending. For our simulations, we use BGPi, a widely used open source BGP security simulator, and we extended it to support the policies we evaluate, incorporate the measurement results as just discussed, and track our specific metrics. We have made our extension open source, and you can find the GitHub link at the end of this presentation. We model the internet as a directed graph of ASs and use the CADA dataset to determine inter-AS relationships. We evaluate two attacker models, the spoofing AS model, whose results I will show in this presentation, and the spoofing host model, which you'll have to see the paper for our results. The spoofing AS model simply assumes that an attacker controls an AS from which it can route data packets to all of its neighbors. For our simulation setup, we evaluated multiple scenarios. Specifically, we evaluated traffic engineering methods all together, as well as individually evaluating each traffic engineering method separately. These include export to all, partial export to some, no export to some, as discussed earlier, as well as one which we just call traffic engineering, which is the combined or overall results. For each scenario, we run 1,000 trials with 5 destination ASs. For each trial, both the legitimate origin and the attacker are selected from the set of multi-homed edge ASs. We vary the percent adoption of SAV policies from 0 to 99% of all ASs on the internet. We will show results for both false positive rate and detection rate alongside a 95% confidence interval. With export to all, this is the default assumption in many prior works and represents the best case scenario for SAV policies. There's no multiple prefixes to handle or missing path information as there would be with no export to some. This is reflected in the results as strict URPF is the only policy with false positives. All other policies have been made to handle the asymmetric routing conditions of the internet and therefore have no false positives. For detection rate, strict also leads in this category, although there are some policies which follow close behind. EFP, specifically the version with bilateral peers, BAR-SAV, and feasible path all have 0 false positives while having a relatively comparable detection rate. So if the internet didn't do any traffic engineering, then we all would be well, and we could deploy one of these. However, as we saw with both our measurement and survey, traffic engineering is widely used on the internet. Looking at the detection rate first this time, you don't notice much, if any, difference from the previous results. And this sort of is just because of One, the attacker model does not change throughout these simulations. And two, traffic engineering methods deployed by the Origin simply don't have a strong effect on the attacker's success rate. As for a false positive rate, you'll notice much more of a change. Strict URPF has increased detection rate. Feasible path has increased false positive rate. And all other policies, in fact, do have some percentage of false positives. If we look at the zoomed in version, we'll see that EFPA, both variants, have 0.6% false positive rate at full adoption. EFP-B and BAR-SAV are slightly lower at 0.4. And in order to achieve no false positives, we need only the Origin to adopt ASPA. No broader adoption of ASPA is required, only the legitimate Origin is needed. Why is this the case? Well, I omitted partial export to sum results for the time constraints. It showed that both strict and feasible path were the only ones with false positives, which sort of points at the fact that no export to sum is really the issue. And since we observed very little no export to sum in our measurements, there's very little in these simulations, hence these low percentages. If we look at specifically no export to sum, we can really see the impact. All policies, if you don't have ASPA or anything like that, you have extremely high false positive rate. Strict reaches nearly 60% at full adoption, and even the best performing policy of BAR-SAV reaches up to 13% adoption at 13% false positive rate at full adoption. In order to eliminate false positives in the no export to sum scenario, you need the Origin to adopt ASPA. Since BAR-SAV is the only policy which leverages ASPA, this makes it the logical choice for adoption, and of course, as you can see, has no false positives while still maintaining a relatively competitive detection rate to that of strict. Finally, DSR represents a slightly different challenge. Rather than having limited route visibility as you would with no export to sum, you're having a situation in which an Origin routes packets with a IP prefix it does not announce. From a policy standpoint, this is identical to spoofing. However, this is, of course, a legitimate routing configuration that's used by CDNs. So how do we handle that? This is where ROAs come in. When an edge server wants to respond with a source IP prefix that it does not announce, it just needs to have a ROA authorizing its use. With that, BAR-SAV can then validate this traffic. One thing you'll notice is this graph looks slightly different than the ones previously shown. This is just due to the spoofing host versus spoofing AS results. Here, since we assume that this is a legitimate routing configuration, we don't assume a malicious AS. So they are just routing down the best path. However, for previous results, since we assume a malicious AS, they are routing to all neighbors and seeing if any of those routes can reach the destination. Thank you all for attending my talk. I appreciate it immensely. If you have any questions, I'll be happy to answer.